Hello guys, so we are back with a new problem from TensorTonic. So today's problem is compute Silhouette score. Now Silhouette score is kind of a standard metric for evaluating clustering clustering processes. So we know like there are various algorithms like k-means, db-scan, there is some algorithm methods also. So there is also umap involved. So all that clustering algorithm will give you clusters, okay, but we need a metric to evaluate those clusters, okay, and this Silhouette uh, score is one of the metric, okay. So to tell you like how it works, okay, so for example, let's say we have some clusters, okay, so let's say I choose this color, we have some points like this, okay, like this, and let's say we have another cluster like this, okay, and let's say we have some other clusters like this, okay. This is not at all visible, let's choose purple, okay. Let's say we have some cluster like this, okay. So what Silhouette score does is, so Silhouette score basically first act for every point, okay, in the whole data set, okay. If I consider this data set, okay, let's say I choose this point, okay, let's say this is the ith point, okay. So what it does is it calculates two kinds of distances, okay. One is like cohesion distances, cohesive distances, okay. These are just like industry standard words, but the meaning of it is pretty simple, okay. And another is you can say like adhesive distances, okay. So if you guys are like are aware of like capillary actions, we have heard these terms later in our earlier in our high school, right? So cohesive means like something kind of intra, okay, and adhesive means something kind of inter, okay. So what cohesive distance basically means is, so if I consider these three clusters, okay, let's call this cluster as C1, okay, this cluster as C2, okay, and this cluster as C3, okay. So for this ith point, I will be calculating the cohesive distance first, okay, which is given as this a of I, okay. Now the definition of cohesive distance is average distance to all other points in the same cluster. So what that mean is, if this is this point, okay, I'll be considering this distance. Let's consider d1, okay, this distance d2, okay. So this point is not okay, okay. So let's say there is d3, okay, and let's say, so basically all the distances, okay, in the same cluster, okay, and like that, okay. So if I write the mathematical representation, okay, it is basically the average distances of a point to all other points in the same cluster, okay. So let's say if I designate some Cith cluster, okay, this will be my normalizing constant, and here I will be basically calculating the distance between my ith point to the jth point, okay, where j is a point belonging to the Cith cluster, okay, and j should not be equal to I, okay, and this I'll be going towards the number of points I have in the cluster, okay. So this is the mathematical representation, okay. Now here d is usually taken as a Euclidean distance, okay. So yeah, so this will basically tell me like for a given point in the cluster, okay, how much related are those points are, okay. So if you want the intuition, so this basically means that, okay. Now there is adhesive distance, okay. Now what this adhesive distance is, so for this point, okay, this ith point, so I will consider all those points, okay, which are not inside the cluster, okay, basically all other points in other clusters. Okay, so for this point I'll be considering this distance. Okay, let's call it d2 1. Okay, then d2 2 I'm saying for cluster 2. Okay, d2 like that. Okay, and what I will be doing is I will be calculating the mean distance, okay, over all the points with respect to this point. Okay, so that will basically give me an idea of what is the distance of this point to this cluster. Okay, so you can consider, like, you can make a sense, like if I consider the centroid of this cluster, okay, what is the distance of that, okay, to this point. Okay, so let's call it d2 average. Okay, then I will do the same thing for this cluster also. Okay, let's call it d3 average. Okay, so I'll be finding all these distances for all other cluster, okay, excluding my current current cluster. Okay, and then I will take a minimum of it. Okay, so what I'm saying is, okay, let's say I have some let's say m clusters. Okay, if I have m clusters, okay, I'll be calculating the average distance. Okay, which is basically again summation of d of my ith point to the jth point in the cluster. Okay, and basically j belong to some cluster cj. Okay, and I'll be normalizing over the number of points in this cj cluster. Okay, and I can write like cj should not be ci, cj should not be equal to, or I can write it somewhere else. Okay, cj. Okay, and I'll be considering the minimum of this. Oh, see, yep. So let's forget about m clusters. Okay, so this will represent these distances. Okay, and I'll be considering the minimum of them, minimum such that cj should not be equal to my ci. Okay, so this is the adhesive distance. Okay, and what this additive distance will do is, so for a point, okay, so it will give me the best cluster which is closest to this point. Okay, now I will be considering that cluster to evaluate how the cohesion is with respect to this point in its own cluster. Okay, so for example, okay, let's say I have this point. Okay, let's say this point belongs to some this kind of a cluster. Okay, and now let's say I have another cluster which is something like this. Okay, so if you see here, okay, if I capture the centroid of this, okay, and the distance of this centroid to this point, okay, now this distance will be lesser compared to the average distance of this point to its own point in the cluster, like to all other points in its own cluster. Okay, so if I say d of cohesive, okay, this will be higher than d of adhesive. Okay, for my ith point, okay, for this point. Okay, now what this will tell me is, maybe I should reevaluate my clustering. Okay, maybe this point belongs to this cluster, not this cluster. Okay, then I will again run my clustering algorithm. Okay, or I will tune some parameters to reassign the clustering indexes to all these points. Okay, so by this way I'll be getting a relativeness, like how better is my you can say like my clustering algorithm is. Okay, so yeah, so here the problem is like that only, we have to create this Silhoutte score. Okay, now one more thing we can also find from Silhoutte score is, okay, I guess you guys have heard about elbow method. If you guys haven't heard about it, you can search in Google or read some paper. Okay, so this elbow method basically tells us like so basically, so generally in unsupervised learning, okay, if you want to cluster the points, generally we do that so that we can find a relation between all the data points that we have, okay. Do they have any pattern in them, okay? Can we put a classification kind of a problem over that, okay, something like that. So in order to do that, we have to find a k, okay, like how many clusters should we consider, okay. So generally people go with elbow curve, okay. It basically gives you a you can consider like a negative logarithm kind of a curve, okay. I will search for elbow curve, okay. And wherever the loss is minimum, and so we consider that k value, okay. So we also experiment with some other k values, so you can see like 6, 7, 8 are giving the minimum losses, okay. So we will test out with like 6, 7, 8 clusters, okay. Then we will see like which cluster we want to go with, okay. So elbow method is one, okay. Another thing that we can try out is, so we can do this Silhouette score thing, okay, and we can, let's say, iterate from some k in range so this is a hyperparameter, okay, from, let's say, from 1 to some max amount, okay. And we can cluster out those points, okay, cluster points, okay. Now for each of our cluster, we will compute the Silhouette score, okay, and we will see for which k we are getting the maximum clusters like Silhouette score, okay. So for which k Silhouette score we are getting the max Silhouette score, okay. So with this we will get a better k, okay. Now the things that we have to consider here is, now Silhouette score consider like this Euclidean distances, okay. Now it may happen, okay, like this metric is not always like give you a better like the best k, okay. Let's say I have some kind of a cluster like this, okay. Let's say I have points like this, like oriented in this circular fashion. Let's say I have another cluster like this, okay. So in this kind of clustering problem, Silhouette score might be unstable, okay. It may not give you a good clustering representation or the best k value, okay, because here Euclidean distance metric will fail, okay, because the metric assumes that like the clusters are well separated like that, okay. But if I consider a point here, okay, and a here, okay, so the average distance that I will get in this cluster will be always be higher compared to the adhesive distance, okay. Considering this, or it should be from the centroid, okay, considering this distance, okay, with respect to the cohesive distance of this point with respect to all other points will be like basically d adhesive will be very much lesser than d cohesive, okay. Now this will become this algorithm unstable, okay. So we may not find good k values here in this kind of case, okay. So yeah, so we just have to like plot the points and we have to see whether we are getting better clustering algorithms, okay, like better clustering with the k. So but yeah, there are many applications of this algorithm, okay. It is still being used in recommendation system or in image segmentation kind of a task, okay. So people generally try multiple like clustering algorithm and then they select one of the like one of the clustering algorithm that works for them, okay. It really depends upon the data set, okay. But yeah, so Silhouette score is one of the metric, so it's not always giving you the best, but it can help you with your data set. Cool. So if I look at the yeah, this diagram here, okay, as you can see, okay, we are getting a Silhouette score of 0.679, okay. But if I bring this cluster closer to this cluster, okay, you can see like we are going in the negative direction. Yeah, so on this only, so yeah, so here you can see, okay, we got this cohesive distance and adhesive distance, okay. So what then we will be doing is, for every point we will be calculating the Silhouette score, okay, which will be the uh, adhesive distance minus the cohesive distance of that point normalized by the max of bi and ai. Okay, now this will be doing for all the points. Okay, now for our whole data set, okay, we want only one metric, right? So we will be taking this mean of this. Okay, so the Silhouette score will come out to be mean of, okay, which is basically the number of points that we have, okay, summation of all the Silhouette score that we got, and s of I. Okay, so this will give us like one number. Okay, now the range of this will be -1 to 1. Okay, so yeah, as you can see, like here we are getting a Silhouette score of negative. Okay, which basically means that maybe not all points belong to this cluster. As you can see, like I can see a overlap here. Okay, so this point is belonging, like, is inside this cluster, that's why you're getting negative. But if we have well separated points, okay, so if I bring this guy to a far distance, now you can see we are getting a good Silhouette score, which basically means our clusterings are good. Okay, so yeah, cool. So now I guess you guys have a better, like, good idea like what is this Silhouette score for, and where all applications, like where all things we can apply it. Okay, now let's solve this problem. Okay, now here the problem is like we have been given the points, okay, the Cartesian coordinates of the points, okay, and we have been given the clustering indexes, okay, like they are telling us like labels, okay, which basically means like for every point it tells us like which cluster it belongs to. So for this first point it belongs to 0, the second point belongs to also like 0th cluster, okay, and like that. So here we can see like we have been given 2 clusters. Cool. So now I will basically tell you like how I will be implementing it. Okay, now the challenge here is like we cannot use for loop. Okay, so all these operations what we will be doing all needs to be like vectorized. Okay, so instead of doing for looping we should use some linear algebra stuff to compute our Silhouette score. Okay, so yeah, so I'll first tell you like how we will proceed. Okay, so we have been given this points. Okay, now first thing first, okay, we need to get the distances first, right? For every point, okay, we first need to get the distances, okay, the Euclidean distances. Okay, so how to get it? Okay, so what we can do is, okay, we have been given this points. Okay, so I have this points. Okay, and so we can first say something like this. Okay, first Euclidean distance for all pairs of points. Okay, cool. So how to get this? Okay, so if I draw this x, what we have been given, okay, let's say d1 d2 something like this. Okay, so we have been given this points, which is a list of points. Okay, let's say p1, p2, p3, p4, I like that, some pn points we have been given. Okay, where pi is the x coordinate and y coordinate, right? Cool. So how can we do it? Okay, so we can see we can use NumPy. Okay, now in NumPy we have this algorithm which is like np linealg norm. Okay, now we know the norm of a vector is basically a normalized, or basically like a Euclidean normalization, or you can say the L2 norm, right? So for example, I have xi and yi. Okay, let's say I have this vector. Okay, so line norm will give me xi square plus yi square, a square root of it. Okay, cool. So we can use this API from NumPy to get the distance. Okay, now how to get it? Okay, so what we can do is we can broadcast these points. Okay, so what I mean by is, so basically we need some kind of a difference, right, of these points. Okay, so for example, for P1 and P2, if I want to get the distance, what I will be doing is I'll be taking x1 minus x2 square plus y1 minus y2 square, and then I will take this norm. Okay, so how to get it? So what we can do is we can broadcast points first. Okay, now how I can broadcast? Okay, so what I can do is I can transform these points into two forms. Okay, so the first form will look something like this. Okay, I can apply a dimension over all the points. Okay, P1, P2, P3, like that. I can transform the Pn point something like this. Okay, now another broadcast that I need to do is, okay, that is I will expand the dimension, the outer layer. Okay, so what I will be doing is I will I will basically add one more axis over this whole points. Okay, so it will look something like this, and like that to Pn. Okay, and yeah, assuming like I have already converted points to a NumPy array. Okay, now if I have these two transformations, okay, now let's say this is some transformation, let's say call it T1, and let's say this transformation, let's call it T2. Okay, so what will happen is, so if I do T1 minus T2, so how NumPy will interpret is, so for each of this dimension, okay, so for each of this element, I have to get the subtraction or the difference of all these points. Okay, so for P1, P2, P3, like that I have, okay, up to Pn. Okay, if I subtract P1, P2, P3 till Pn, okay, I'll get a matrix of something like this. Okay, so P1 minus P1, P2, P3 up to Pn. Okay, then second thing I will get is like P2 minus P1, P2, P3, oopsie, okay, till Pn. Okay, and like that for Pnth point. Okay, the broadcast will do something like this, right? Now this operation will be applied point wise. Okay, so I'll get a final matrix which will look something like this: P1 minus P1, P1 minus P2. Okay, so I'm not putting commas here, but there are commas in between. Okay, okay, because if you print a NumPy array, they usually don't put commas. Okay, so yeah, I'll just stick to this P3, and like that P1 minus Pn. Okay, now if you see here, I'm getting the difference of coordinates, okay, for every point to all other points. Okay, like including that point also. Okay, like that I will get Pn minus P1, okay, and Pn minus P2, okay, and like that Pn minus Pn. Okay, now I have this matrix. Now if I apply NP line alg, or if I take the let's call this as a diff. Okay, let's call it diff. Now if I take the norm of this diff, okay, now what it will give me is, so this norm operation will be applied over each element in this diff matrix. Okay, so this will give me P1 minus P2 norm, P1 to P1 norm, again p1 minus p2 norm, okay, and similarly p1 minus pn norm, okay, which is basically the Euclidean distance here, okay, like that, okay. So yeah, let's first implement it, okay. So first I need to convert the x and the labels, okay, into NumPy arrays. So x labels, I'll be using map function, okay. So I'll say np dot array and I'll say x labels, okay. So now they are converted to NumPy arrays, okay. Now I'll get the transformations here, okay, or I can directly get this distance, let's call it distance, okay. This distance matrix, let's write it clearly, distance, okay. So I got x, okay. So what I will be doing is I'll say dist equal to np line alg, okay, dot norm of x, okay. So I was expanding a dimension for every point, okay. So I'll say consider all the points, okay, introduce a new axis over each point, okay, this, okay, subtracted with x, and the second transformation I was applying is over the whole points array, okay. So I'll say np new axis colon consider everything, okay, cool. Now when I'm considering the norm, okay, so I don't need to take the norm in this manner, okay. So I need to consider them individually, right? So I'll be saying axis 2, okay. Now let's print this distance, okay. So y axis 2, okay. So if I expand this, okay, if I expand this, okay, this will look something like another array where I'm doing x1 minus x2, okay, and I'm doing y1 minus y2, okay. Now if you see the dimension, okay, now the first dimension like axis 0 is this, okay, or let me write axis 0 is this, okay, axis 1 is this, okay. Now this is where axis 2 is, okay. So axis 2, okay. So that's why, so we have, you can say, 3 nested list, okay. So I need to consider the innermost list, okay, which is axis 2 here, okay. Now if I print this, okay, so dist, let me put some new lines first, dist new line, and I will say dist, okay. If I print it, okay, so it throws an error like I must return a float, okay, because I'm not returning anything, okay. But yeah, as you can see, I got the distances, okay. So for every point to point, okay, I got that Euclidean distances. Now if you observe the diagonal or the main diagonal of this matrix, they are all 0 because that's the Euclidean distance from the point to itself, okay. That's why they are all zeros, okay. But yeah, with this I got the distances, okay. Now second thing that we need to consider, okay, so we need to consider so the second thing that we need to find is this cohesive distances, cohesive distances, okay. How to get the cohesive distance for a point, okay. Now cohesive distance definition, as we have seen somewhere here, okay, which is the number of points in that cluster, okay. So basically the distance of all the points with the current point that we are considering, okay, the sum of that normalized over the number of points we have in the cluster, okay. Now here the thing is, this normalization is like not the all the points that we have to consider, okay. We have to do a -1 here, okay. Why? Okay, so if you see, okay, why cannot I go? Okay, so let's say we have 3 points in a cluster. Okay, so how many distances I will be getting? Okay, so if I consider this as my ith point, okay, so I'll be getting two distances, d1 and d2. Okay, so total number of distances that I'm getting is basically number of points I have minus 1, right? So if I want to take the average of the distance, okay, I need to consider the total number of distances that I'm getting in the cluster, okay, which is basically the number of points I have in the cluster minus 1. Okay, so that's a minus 1 here. Okay, cool. Now how to get it? Okay, so in order to get it, we need to do few things. Okay, so the first thing is we need some kind of a mapper, okay, that can directly tell me, okay, for each point, okay, where they belong, like which cluster they belong to. Okay, so for that what I will do is first I need to get the number of clusters that I have. Okay, so I'll say clusters. Okay, then I will say a cluster mapper. Okay, okay, and I'll say np unique. Okay, and I will say labels. Okay, and then I will say return inverses. Okay, now what this return inverse will do is, okay, this will give me this cluster mapper. Okay, now this cluster mapper is a matrix. Okay, now what does matrix basically tell us? So basically I will show you. Okay, so if I print this cluster mapper, so I can copy this print statement. Okay, okay, I can put this cluster mapper here. Okay, and if I show you cluster mapper, okay, cluster mapper will give me something like this. Okay, now what it is doing is, okay, so for every point it is basically giving me the cluster where they like the clustering index of every point. Okay, which is very much similar to the labels. Okay, but how we will be using is, so it's a bit different. Okay, but yeah, just stick with me, I'll show you how we will be using it. Okay, now one more thing that we can apply here is we can find the number of clusters that we have. Okay, so that will be basically len of clusters. Okay, so np unique will give me the unique number of like the clustering indexes. Okay, if I print you that, okay, so basically it will give me an array of 0 1. Okay, as you can see, like we have only 0s and 1 cluster indexes. Okay, clusters. Okay, as you can see, like 0 1. Okay, now for this whole problem, okay, let's say I have been given only one cluster, okay, with only 1 point. Okay, then the Silhoutte score is basically 0, right? Okay, if I only given like something like this, okay, a single point, okay, and this belongs to some 0th cluster, I cannot find any Silhoutte score because there is only 1 point. Okay, so in that case I'll simply return 0. Okay, if k equal to let's say 1, okay, I can directly return 0.0. Okay, because the problem demand is like we have to we must work with like more than 2 clusters. Okay, we have to consider Euclidean distances, we have already considered that, and everything needs to be vectorized. Okay, cool. So if k is like if only one cluster is present, then we have to consider this. Okay, now what we will be doing is we will be considering all the points first. Okay, I need to get all the number of points we have been given, and points. Okay, okay, now so if I consider let's consider an example. Okay, let's say I have been given some points like this. Okay, let's say we have been given p1, p2, p3, let's say p4 and p5. Okay, so I have this dist. Okay, so the dist matrix is basically giving me, okay, the distances between all the points. So d11, d12, d13, okay, d14, d15, okay, and like that I have been given like d51, d52, d53, d54 and d55. Okay, now I need to apply some kind of masking here, okay, so that I will only consider those distances which belong to uh, a particular cluster. Okay, so for a point, okay, I need some kind of masking that can tell me for this point, okay, if I know the clusters, like the cluster index, okay, now what all distances in this matrix or what all elements in this matrix we have to consider. Okay, so for that what I will do is I will create a mapping index. Okay, so what I will do is I'll consider all my, so basically I will create a identity matrix, okay, with respect to the number of clusters I have, which is k. Okay, then if I show you this, okay, this will give me m n m. Points. Okay, so points instead of points we have given this. Okay, so if I run this, okay, so I got something like this. Okay, now I can use my cluster mapper here. Okay, from that I can basically tell for which point, okay, I need which row in my this I matrix. Okay, so I will simply say cluster mapper. Okay, cool. So as you can see here we have two clusters. Okay, so for the first point, okay, you can see the first index I'm getting 1 0, or the first row that I'm getting is 1 0, which basically means that if you see in this row the first element is 1, that basically means this point, okay, belongs to 0th cluster. Okay, so here M matrix basically designates points to cluster. Okay, and this is of a shape number of points we have and k. Okay, cool. Now what I need is I need the distances in of a point in all the clusters, right? So for that what I will do is, okay, I'll take this D matrix, okay, and I will do a cross product with respect to my point to cluster mapper. Okay, which is basically M. Okay, so for example, okay, let's say we have this 5 elements. Okay, now let's say we have been given labels something like this. Okay, let's say 10, 20, okay, 30 and 20. Okay, so if I look at the unique labels, okay, this is 10, 20 and 30. Okay, then the cluster mapper that I will get, okay, let's call it cluster mapper. Okay, I'll get for all these labels, okay, what is the mapping for that? Okay, so this will be 1, sorry, this will be 0. Okay, this will be again 0. Okay, this will be 1, this will be 2 and this will be 1. Okay, so if you see here we have been given binary like binary indices of the clustering. Okay, but they have told us like something here, distances must work for any number of clusters k more than 2. Okay, so there are no hard constraints like what all values we can get in the labels. It may happen like they have given some unique indexes to the labels. It's not always like we will get 0 to some k indices in the labels. Okay, it can be 10, 20, like 10, 10, 10, 20, 20, something like this, or maybe 100, 101. Okay, those are basically indexes can be anything. Okay, what this cluster mapper will do is it will give us a vector which have element between 0 to the number of clusters we have. Okay, so using this cluster mapper we have this. Okay, Now uh, now for this data, okay, if I construct the M matrix, okay, so this will be something like this. Okay, we will have a matrix where for this point, okay, I will have 1 0 0. Okay, now how I am constructing M, as you can see. Okay, okay, so first I'm creating an identity matrix of size like if I draw K here, K is 3. First I'm doing an identity matrix of 3 cross 3, okay, which is like 1 0 0, then 0 1 0, then 0 0 1. Okay, this is our identity matrix. Okay, then I'm applying a filter, you can say. Okay, so what this is basically saying is, okay, so for my first index, okay, consider the first row, okay, 0, or the 0th row. Okay, for my second point, consider the 0th row. Okay, and for my third point, okay, so basically these are like indexes, right? 1 2 3 4. Okay, when I am applying over this cluster mapper, I'm basically extracting out what all rows in this identity matrix I have to consider for the points. Okay, so when I'm applying this to operations, okay, what I'll be getting is for all the points which row in this identity matrix I need to consider. Okay, so if I go down again, okay, so I'll get for the first point, which is this. Okay, this has a cluster mapper index of 0, so I need to consider the 0th row of this identity matrix, so it will be 1 0 0. Okay, similarly for the second point, its cluster mapper is 0. Okay, so I again need to consider the 0th row of this identity matrix, so which is 1 0 0. Okay, then for the third point, it is 1, which basically means I need to consider the 1 index row, which is this 0 1 0. Okay, and like that, if I continue, it will be like 0 0 1, and similarly it will be 0 1 0. Okay, like that. Okay, now as you can see, the number of elements here is number of points that we have. Okay, okay, and the number of columns we have is basically the number of clusters that we have. Okay, so if I take any ith point here, okay, and I look at which cluster index is set. Okay, so if I consider this, okay, for the third point, I'm seeing the one index in the column is set, which basically means my third point belongs to the one index cluster. Okay, which is 20 here. Okay, cool. Now if I do a cross product with it, okay, what I will be doing is I will be considering distances to all the clusters. Okay, so if you see here, okay, if I substitute, or let's say for this, the M is basically this. Okay, if I do this, okay, and if I do a cross product, okay, so I'll be getting a matrix. Okay, let's call this dist matrix. Okay, this will be of shape, okay, this is points, okay, and this is also points. Okay, I'll be getting points cross number of clusters, right? Because this is a number of points cross number of points matrix, this is a number of points cross number of cluster matrix. Okay, if I do the cross product, okay, I'll get number of points cross number of clusters. Okay, now what will happen in this matrix is for every point, okay, or let's say for this some pith point, what will happen is it will store the sum of distances. Okay, it will store the sum of distances to all the points, okay, to all the points in my jth cluster. Okay, so I can say something like this. Okay, so for a pith point, okay, in this cross product matrix, okay, if I consider this ith row, which is basically designating the pith point, okay, So it will consider the sum of all the points of this ith point, okay, with respect to the jth point, okay, in my jth cluster, okay, the sum of all the distances, okay. Similarly, d of let's say j1 j1th cluster, okay, similarly I j2, okay, like that, okay. Now this matrix will make my life pretty simple because I'm directly getting, okay, the sum of distances of all the points, okay, in individual clusters, okay, with respect to every point, okay. Now I can apply some masking, okay, in order to get intra distances and or in order to get like inter distances, okay. So yeah, that's what I will be doing. So first thing first, I will name it as this. We did Euclidean distances. Okay. Then next thing, we'll get cluster distances, like point to cluster distances. Okay. This I'll get like cluster disks. Okay. So this cross product I'm giving a name like cluster dist. Okay. So this will be dist @m. Okay. Now if I print this, okay, as you can see, so what you are seeing here is for this point, okay, for my first point, okay, I'm getting the the summation of all the distances in its own cluster, okay, and the sum of all the points or the summation of the distances for this first point with respect to all the points in the first index cluster, okay. I hope it makes sense, okay. So if I show you here, okay, this, or if you guys are confused, okay, so this 22.69 is basically distance of my 0 0, okay, and 5 5, okay, plus distance of this 0 0 and 5 6, okay, plus distance of 0 0 and 6 5, okay. So this 22.69 is this value, okay. Cool. So I hope you guys got the intuition, okay, and the reason why I'm doing the cross product, okay. It directly gives me the summation, okay. So yeah, now I got the cluster dist, okay. Now if I compute the cohesive distances for every point, okay, so cohesive distances, okay. So what I'll be doing is I need to create a cluster mask, right? Okay, I already have a cluster mask using this mapper, okay. So I'll say I'll create something like this, point to cluster, or I can directly get like some mean intra dist, okay, which is like this cohesive distance is basically cluster dist, okay. Here I will apply NumPy arrange n, okay, and apply cluster mapper here, okay, and yeah, and then I'll be dividing with respect to the number of distances or the number of distances in that in its own cluster, okay, which will be np maximum of, okay. So I need to get the number of distance like the number of distances that I will be getting in this cluster, okay. So for that I can create something like this, point to cluster size point to cluster size mapper, okay, and I can say I need to create some cluster sizes, okay. This I can create, and I can bring cluster mapper here, okay. Now cluster sizes I can create, okay. So this will be basically np of sum of m axis 0, okay. So basically if I have this, okay, so I know this is 0th cluster, this is 1 cluster, this is 2nd cluster, okay. Now if I take the summation in this direction, okay, that will basically tell me for this 0th cluster how many points I have, okay. Now similarly for this one index cluster, how many points I have, like 2, okay. And for this second cluster, how many points I have, which is 1. As you can see here, we have this, okay. So this is axis 0, okay. So I can also print this for you guys. Cluster sizes, okay. Now once I have cluster sizes, I am applying the cluster map. So for every point, okay, I will have a matrix, okay, that will basically tell me, so if the point belongs to some cluster I, okay, what's the size of it, okay. So I'll say point this, okay, cool. Now why I need it is because for normalizing, okay. As you can see, cluster sizes is this, and somewhere I didn't got this cluster sizes, yes, okay, cool. So point to cluster size. So for the first point, okay, it belongs to this 0th cluster, and the 0th cluster has a size of 3, okay. Why I need it? Because using cluster distances, okay, I'm applying a filter of np arrange n, okay, because in this cluster dist, okay, if I go in the diagonal manner like this, okay, I'm basically saying for this ith point, okay, it belongs to, I need to consider this element, basically the first row, okay. And so now cluster mapper will tell me what all like what all clusters I should consider, okay. So it's for that, okay. So if you guys are confused, it's basically like I have, so for each point, okay, I am getting the summation of the cluster distances, okay, like this, okay. Now when I'm doing np arrange, okay, what I am doing is I'm basically applying a filter, okay. What like for my ith point, which row to consider, okay, this is for that, okay. For my ith point, which row to consider, which is basically the ith row, okay. Now in that ith row, okay, what all values to consider, okay, that I can get from cluster mapper, okay, because my cluster mapper is something like this, okay. This is my cluster mapper, right. Sorry, this is my cluster mapper, okay. So yeah, so this will give me the intra cohesive distances, okay. Now I need to take the average, okay. Now I will average out with respect to the number of distances that I will that I am getting, okay, in that cluster, okay. So I'll do a np maximum to get a the point wise maximum comparison, okay. Now it may happen we have been given only 1 point in a cluster, okay. So what I need to do is I will be taking cluster sizes here, okay, cluster sizes, okay. Now in this cluster sizes, I don't need to, because I created this point to cluster, okay. I'll be doing a -1, okay, cool. Because point 1 belongs to this 0th cluster. Now the 0th cluster has 3 points, okay. So the number of distances that I will be getting is 3 minus 1, okay, so 2. Now if it happens like one of the cluster has only 1 point, okay, now for that point this value will be 1, okay. Now when I'm doing 1 minus 1, I will get a division 0 error, okay. So in order to accommodate that, I'm doing a maximum comparison of 1 and 0. So yeah, so with this I am getting the cohesive distance. Okay, now if I show you this, I'll print cohesive distance, or this. Okay, cool. So for all the points I got the average cohesive distances. Okay, so I can do a quick check. Okay, I can see like all these points belong to the same cluster. Okay, now for this point, okay, if I consider the distance, okay, so 0 comma 0 distance, like it's just Euclidean distance from 0 comma 1, it's 1. Okay, then similarly its distance with respect to this point is also 1. Okay, so the summation of distances I'm getting 2. Okay, and the number of distances I have 2. Okay, so 2 upon 2 is 1. Cool. So like that we have to do it. Cool. Now I need to consider adhesive distances. Okay, so next task is adhesive distances. Adhesive distances. Okay, so what I will do is, now since I have this, okay, this cluster dist, okay, which are already giving me for a given point the summation of all the distance, okay, with respect to every cluster. Okay, I can directly apply an average here. Okay, so I can create an average cluster dist. Okay, so this will be cluster dist divided upon cluster sizes. Okay, so all this will get normalized with respect to all the points. Okay, in their respective clusters. Okay, so this 2 will get normalized to 3, like normalized by 3, because in this cluster I have 3 points. Okay, now similarly for my one index cluster, okay, I also have 3 points, so this will get divided by 3. Okay, cool. So now if I print this, average cluster dist, I put this at a space. Cool. So you can see this 2 gets divided by 3, I got 0.666, and this 22.69 get divided by 3, I got 25.56, like 7.56. Cool. I got this average distances. Now I can easily compute like the you can see the adhesive distance, okay, for every point. Okay, cool. So what I will be doing is I will create a mask. Okay, so that when as we saw here, okay, when I'm considering adhesive distance, okay, yeah, when I'm considering adhesive distance, I should not consider the point's own cluster, right? I should consider all other clusters. Okay, so what I will do is I will apply a mask. Okay, I will create a mask, let's say self cluster mask. Okay, and here what I can say simply say m equal to 0. Okay, so m was giving me a filter for every point, like to its corresponding cluster. Okay, if I do an inverse of that, okay, basically I will get what all clusters to consider, okay, in order to get the adhesive distances. Okay, so if I print this self cluster mask, so it will put a false value over its own cluster index, okay, for every point. Okay, so as you can see, so using this mask I can say, okay, when I'm calculating the adhesive distance, I don't need to consider this distance value, I need to consider this. Okay, so similarly I can do for all the points like this. Okay, so you can see like these things are reversed. Okay, for all the 0th index cluster points, I'm considering 1 index cluster points, and for every 1 index cluster points I'm considering 0th index cluster point. Okay, now I'll do a inter cluster dists. Okay, similar to what I did here, okay, which was like intra cluster dist. Okay, I'll do inter cluster dist. Okay, I'll first apply the mask. Okay, np where self cluster mask. Okay, and I will do average cluster dist. Okay, okay, so I'm saying wherever I have true in my cluster mask, okay, consider those values from average cluster dist, okay, like 7, 6, this 6.89, okay, this 6.62, 7.36, okay. Now wherever this guy is false, okay, I'll be putting a very high value, okay. I'll put like np inf, okay. Why? Because I need to consider the minimum adhesive distance, right? Okay. So using this, I'm getting for a point to all the summation of distances in every cluster, okay. Now the average of this distance, okay, like among the average of this distances, I need to consider the minimum of them, as we saw here, like d2 average and d3 average, whichever one is like minimum, I need to consider that adhesive distance for this point, okay. So yeah, now I can simply do minimum comparison. I'll say min dist or like min inter dist. It will be np min of inter cluster dist, okay. And I need to consider axis 1, okay, because for every point I have rows. Now for every row, okay, I need to consider the minimum, okay. So let's print this lines, okay, this one and this one, okay. Now if I print this, cool, as you can see, intercluster distances, I'm only considering these distances, okay. And for mean interdistances, I'm doing a comparison of this infinity with respect to this value, okay. So the minimum of them here is like 7.56, so that's all values that I'm getting, okay. So cool. Now for every point I got their corresponding adhesive distance, okay. Also for every point I got the mean intra distance, okay. Now I can easily calculate the Silhoutte score for every point, okay. So I'll say Silhouette score, okay. So I'll say numerator, okay. This will be as we can see the formula, I need to subtract this mean interdist with mean intradist, okay. And for denominator, okay, I need to consider the max, okay. And since I need to do a point wise comparison, I'll be using np maximum, mean interdist and mean intradist, okay, cool. And yeah, I will do a point wise division, okay. So I can say point wise S let's say S score, Silhouette score is basically numerator by denominator, okay. So if I print this, new line, this colon new line, okay. And if I print this, cool. So for every point I got their corresponding Silhouette scores, okay. Now the problem basically tells us like we have to take the mean of all the point wise Silhouette score, okay. So that I can simply do return point wise Silhouette score, and I can take a np mean, okay. And boom, it got accepted, cool. Now this also tells us like we have to return a float value, okay. Somewhere it has told me like we have to do float value, okay. It doesn't, okay, cool. I can submit, and boom, all test cases pass, cool. So this was about Silhouette score, okay. I know the video is pretty long, but like my thinking was like all these NumPy operations are necessary to understand, okay. Why, like how cross product is helping us, okay, and how this point to cluster mapping is helping us as a filter, okay. All those things were necessary, okay, to understand. And how we created this Silhouette score function without using a single for loop, okay. Everything is vectorized here, okay, in NumPy. And yeah, as you can see, there is not a single for loop or a while loop we have used. So yeah, this was about Silhoutte score. So if you find the video intuitive, okay, please put a like in the video, and please do subscribe to the channel. I'll be solving more TensorTonic problems, okay. And yeah, you can also go to this platform. It's a very good platform, like it's similar to like lead code for ML engineers, okay, and the problems are pretty intuitive, and most of the problems you have to solve using NumPy, so that's quite interesting. It will help you to understand NumPy core functionalities and how you can use them, okay. And yeah, that's all for this video. So thank you for watching. Bye bye.